HTERT is effective in rejuvenating cells, we need to develop methods to get the RNA into cells in vivo. So the major hurdle for this RNA therapy and most other RNA therapies is delivery. So we're working with our nano colleagues to develop methods for systemic delivery. So that's going to be a big hurdle to overcome. In the meantime, for other disorders, the low-hanging fruit for us is to rejuvenate cell therapies where we can use electroporation or some other means to get the RNA into cells. So in that case, that would be ex vivo. So we wouldn't have to do that systemically. We can treat cells ex vivo. For example, cancer immunotherapy, T-cell immunotherapy, we may be able to improve with HTERT. And what we have funding from this institute to improve immunotherapy for neurodegenerative disorders. So Stanapel has data that T-cell therapy, Treg therapy can be useful for ALS. So we're going to improve that therapy with telomerase, RNA telomerase, using electroporation.
Thank you. I would like to ask also Gianni. So you mentioned that the IBS from progeria, lack of, it seems to me that lack of ability to differentiate it to a normal endothelial cell, right? So how do we know the role of distal flow on the ability to differentiate from IBS cell to endothelial cell? I think that is critical.
She's asking about why not use shear stress to help you differentiate IPS to ECs, because ECs are responsive to shear stress tractive force.
We definitely, this is a part of the study we would like to help with your help, probably. So we would like to do that. We wanted to completely understand how these endothelial cells derived from iPSC, EGPS patient look like. So the shear stress, we think is an important characteristic. So as you know, we are working now on the optimization of the culture of this cell, and then we are very happy to start a collaboration with you.
But actually, I suggest that first we can look at IBS cell under distal flow. How for example, you can expose the IBS cell from normal and progeria under steady and distal flow, and you see how that IBS cell can be differentiated. I think that might be a good start.
Okay.
Yeah.
Yes, that's a good idea. Thank you.
Okay. So a very simple question. So why the shorter telomere cause this disease? Or why the shorter telomere cause different phenotype of this iPSC induced endothelial cell?
That's a good question. Most people in this field, HGPS field, would point to the abnormal lamin. This is a laminopathy, abnormal lamin A protein. And all of the focus in this field has been directed toward trying to correct that problem, the farnesyltransferase inhibitor, for example. Our approach has been different. Shorter telomeres are associated. Telomere erosion is associated with this disease. So we thought, okay, this is something else that's going to need to get fixed, because you can use a farnesyltransferase inhibitor and prevent further abnormality of the nuclear morphology. But these kids already have short telomeres. Now, your second question is how does a short telomere cause a phenotype? Well, a short telomere is recognized by the cell DNA damage repair machinery as being abnormal. It triggers a DNA damage response. A DNA damage response that accelerates aging. So that's, in brief, a simple answer to your simple, straightforward question. It's a DNA injury response.
I have a question about the progeria disease. So the first question is the lipoprotein profile normal in this patient? And the second question is, as we know, the CHIP is important, the clonal hematopoiesis is an important disease for this atherosclerosis. Does you find some bias some abnormalities associated with hematopoietic stem cells. The third question is, since you mentioned that senescence is a main driver for atherosclerosis, I assume this patient there's homogeneous senescence associated in all the vascular bed, but why is the coronary artery the most sensitive vascular bed to affect, but not stroke? Let's see. Or did you see the lesions distributed evenly around the whole vasculature?
Do you want to answer those questions? As usual, Dr. Fang asks tough questions. So let me take the last one first. And you're wondering about the heterogeneity of the vascular abnormality in these kids. I showed you that they die of heart attack and stroke. And your question is, why don't we see disease in other vessels? Perhaps we haven't looked hard enough. That's one possible answer. I would point out, though, that atherosclerosis in all of us is heterogeneous. The distribution of atherosclerotic plaque, whereas although it tends to occur at bends, branches, and bifurcations, there are areas in the body where it doesn't occur at those sites. For example, in the arm, we have bifurcations. We have disturbed flow in our arm vessels, but you don't see atherosclerosis causing significant narrowings. There's some atherosclerosis in arm vessels, in the brachial artery, for example, but it's very mild. The only atherosclerosis you get really in the upper extremities is in the subclavian artery. People can get subclavian stenosis, but generally the upper extremities are not affected. What is the mechanism for that heterogeneity? We don't know entirely. It may be differences in where the endothelium was derived from embryologically. It may be differences in endothelial functions. There are regional differences in endothelial function. There's a whole book by William Aird from Boston, Beth Israel. William Aird's written a whole book on endothelial heterogeneity. It's in my office if you want to read it. So I hope that answered your third question. Now, your other question was what? Your other questions?
CHIP, the hematopoietic stem cells.
Yeah. So CHIP. Most of us, when you hear CHIP, you think of chromatin immunoprecipitation, but this is a different CHIP. This is clonal hematopoiesis of indeterminate potential. So in older people, you get these genetic defects in the hematopoietic stem cells. Typically in epigenetic modifiers, they've been described in epigenetic modifiers, mutations, somatic mutations that occur with aging. With aging, you get somatic mutations. And some of those mutations can cause tumor, right? Or in the case of blood cells, leukemia. Well, clonal hematopoiesis of indeterminate potential is a mutation in hematopoietic stem cells that does cause an increase in proliferation, but not leukemia. So there's, in those HSCs that have this mutation, typically in an epigenetic modifier, they have a greater proliferative capacity. So that subset of cells tends to expand in your blood pool, and you see the mutation in not all the white blood cells, but in more and more white blood cells over time. Sometimes it can lead to leukemia. Anyway, your question is, is there any relationship between CHIP and progeria? And the answer to that is, I don't know. But that is something that would be interesting to look at. I should say one thing, though, that progeria primarily affects the mesodermal line. Of course, hematopoietic stem cells are in that line. So, I mean, your question is relevant. What happens to the blood in these kids? It doesn't seem to be a major problem. One of the things that happens with aging, in addition to leukemia in older people, is the bone marrow starts getting depleted of stem cells, and they can get anemic or neutropenic. But I haven't seen that reported in these kids. Any other questions or comments? I have one. I'd like to ask the group a question. Johnny showed you very nicely that the iPSCs from these children that are derived from their fibroblasts, the iPSCs look normal. They express all the markers of pluripotency. They express the transcriptional factors. They behave normally. They can differentiate. Others have shown that they can differentiate into all the cells, somatic cells. They can reproduce indefinitely, replicate indefinitely. What's your speculation as to how, what is the mechanism by which these iPSCs seem to be normal? Huh? Telomerase, who said that? Roman. I think that's right. I think that's true. And there's good evidence from a Singapore group that has an ESC line, embryonic stem cell line, that overexpresses progerin. So these cells express progerin. When they're differentiated, the cells from which they're the derivatives look like HGPS cells. They're abnormal. But the ESCs that are overexpressing progerin are fine. They're fine until you knock out telomerase, and then they die. So I do believe the telomerase is the protective factor for iPSCs. I also think it's a protective factor if we can increase it transiently in somatic cells that can rejuvenate these children's cells and could be a great therapy, a more definitive therapy for these kids. So we really want to get this to the clinic.
Okay, other question?
So I have a question kind of related to what Dr. Cook said. You said that the iPSCs from the patient and the normal looks very similar, like they don't have disease phenotype.
Right.
And then Jenny showed some evidence that the iPSC ECs are kind of different between the patient.
Mm-hmm.
So it's quite striking to me, since the telomere has been reset, so why they got this disease again? Like, do you know what is the possible explanation?
We don't know.
You know, that's a great question because, and I didn't actually think of that, because the endothelial cells are abnormal pretty quickly. I mean, they've lost telomerase activity, so they can't extend the telomere. So my thinking was, okay, well, they're experiencing telomere erosion. But you point out quite rightly that there hasn't been a lot of replication between the time you've differentiated the iPSCs into endothelial cells. How many passages does it take between iPSC to EC?
Yeah, normally this cell already start from 20, 30 passage. Normally it take 2-3 passages.
2 or 3 passages.
Yes.
Yeah, so they've had many passages as iPSCs, yes. but they're still iPSCs.
Yes.
But they've only had 2 or 3 passages for us to differentiate them into endothelial cells. So their telomeres become shorter in that period of time. They're no longer making telomerase, so they can't repair their telomeres. So I guess the telomere erosion is pretty fast with expressing progerin. I mean, the Singapore group has seen the same thing with ESCs. You knock out telomerase and they become abnormal very quickly. So that telomere erosion either is happening very quickly or the telomerase has some other protective effect. So thanks for raising that question.
Okay. Thank you so much, Dr. Cook and Gianni, for a good presentation, and thank you for everybody to attend to this meeting.
Good job. Nice job, moderating.